with these projectile problems, I just kind of plan that it's going to take me a full sheet of paper to solve a projectile problem. All the different parts, and so I just kind of plan that it's a full sheet of paper. Personally, if I'm working them out on my own, I really like to use graph paper. And that's just for physics in general. For some reason, I just like to solve physics problems on graph paper. It just seems easier to me. All the little squares, I like that. Um, so let's talk a little bit about these formulas. For projectile problems, you guys are going to use these formulas. Make sure right here. These are our kinematic formulas. I do not want that to be black. It is not. I am like picking a color and it doesn't like it. There we go. And then the important part is that your horizontal velocity is only going to have this formula. So anytime you're working in the horizontal direction, you're only going to use this formula. And the reason is there's no acceleration in the horizontal direction. Okay. Sorry if I cough a little bit. I've been a little under the weather. And this is because, gravity only works, up and down, right? That 9.8 that you guys are maybe starting to accidentally on purpose memorize, it only works in the vertical direction. And so we won't have that that won't bother us in the y or in the x direction, excuse me. And then when we're trying to get the vector velocity, sometimes they'll call this the impact velocity. I like to call it the vector velocity because it reminds me that I need to solve for the vector. And when they ask for the impact velocity and the vector velocity, you need to have like an amount. So you're going to need to have like an amount, like 25, something like that. But then you're also going to need at some sort of angle at like 75 degrees. So the total vector velocity is going to include, this amount or this magnitude, and then also this direction. Okay, so this is our magnitude and this is our direction. And that's why I like to call it a vector velocity, because it reminds me that I need to have, that magnitude part and the direction part, because vectors have both. And then in a horizontal projectile problem, you're always going to want to solve for time first. Even if the problem doesn't ask you for time first, you want to solve for time first. Okay, just always, always, always. Luckily, in this one, I just had to solve for time first, just to keep it a little bit easy. So let's talk about this problem. In this problem, we have a stone thrown horizontally. So that's telling us it's a horizontal projectile problem. And our speed is 5 meters per second. So that's our VIX. And really, that's just our VX, right? Because our horizontal velocity is not going to change. Remember, there's no acceleration. And then we have this cliff that's 78.4 meters high. And then they're asking how long, so that's a time, does it take for the stone to reach the bottom of the cliff? So they've given us two numbers, but we actually have a lot of other numbers. So let's go ahead and write down what we know. We know that our Vx is 5 meters per second. We know that it was thrown horizontally, so that's telling us that our initial y velocity is 0. Okay. That also means that, at some point we'll have a final y velocity. We don't know that yet, though. We also need a time, which that's the thing we're going to look for right now. And we also know that our initial height, we will call that 78 meters. And then we have a final height of 0 meters because it's starting up high and it's going down. Okay, so even though they only gave us these two numbers, we actually have 4 different numbers here. And we can also, I like to draw something like this. And this just helps me kind of think about this projectile. So this is basically a triangle of my velocities, right? So this is my my x velocity to the side. My VIY, I'll put that here. You know, if they were to give me my VFY, I would put that here, and then this would be like our impact velocity. Which they'll probably ask us for in a minute because they do. And then now, so we have a Vx, we have a VIY, and we have a height, and we need a time. So let's go back to our formulas. These are the only formulas that we can use. And if you remember, we need a time, right? So we need this, you know, one of these formulas has a time. We can't use that one because it doesn't have time in it. And then we have these two. Now, this one has a height and this one has a final velocity in the y direction. We don't know our final velocity in the y direction, so we have to use this h one. Okay, so we're going to use the formula hf equals hi plus viy plus 1/2 g t squared. Okay, and now I'm going to just plug in my numbers. So I'm going to do 78. Oh, this should be 78.4. Why did I forget this 4? Okay, we'll have a 0 here. Our y velocity is also 0. And then we have 1/2 9.8 t squared. And I think I forgot a t as well. Yeah, there's a t there. It doesn't really matter, but it's there. And so, you know, this is nothing. This is nothing. And then we have, so then I'm going to just move up here so I don't get stuck at the bottom of this page. And 1/2 times 9.8 is 4.9. And I just have that memorized because I've done so many of these 1/2 times 9.8 problems. So I'm going to get that. And oddly enough, that's 16 even. And so I'm going to just take the square root of that and the square root of that. And my time will be 4 seconds. Okay. So now let's go to the next part. Okay. And remember, we started started with time. So, and also remember, if you're on a piece of paper, you know, that's why I said these tend to take like a whole sheet of paper. I just kind of assume that I'm going to use a whole sheet, you know, front page of a page to do these horizontal problems because there's just a lot. And now this one's asking how far from the base of the cliff. So this is asking for our distance in the x direction. Okay, now let's write all those things that we know again. Our Vx, which was 5, our Hi was 78.4. We're probably not going to need that, but I'll just write it just in case. Our time, we found that out. So I'm going to add that. Our VIY, we're also probably not going to need this either because we're talking about the x direction. Okay, so since we're using the x direction, we're going to use that formula V equals d over t. Okay, and the v in this case is our Vx. Okay, and since we want to solve for d, I really like whenever they ask anything in the horizontal direction because I know I get to use easy formulas. And so I like to put it in the triangle, and so you can see here v equals d over t. And then I just kind of cover up d, and that gives me Vx times t. So I don't have to do any algebra, which I also like. So I'm going to have 5 times 4, and that's just going to give me 20 meters. Okay, so you can see anything in the x direction is really easy because we don't have to mess with accelerations and things like that. So let's go again. So now it's going to ask the horizontal and vertical components of the stone's velocity just before it hits the ground. So that's our Vxf and our Vyf. or VFY, whatever you want to call it. Okay, so let's write what we know. We have Vx is 5 meters per second. We have HI is 78.4. HF is 0. Our time is 4 seconds. We have a horizontal distance now that is 20 meters. And we have a VIY, which is 0 meters per second. Okay, so these are all the things we know. So what's nice about these problems is like the more steps you get into them, the more things that you know and the more kind of possibilities you have open to you because you just know more things about the problem. So the first thing it asks is that horizontal velocity, that VXF. Well, our horizontal velocity, if you remember, doesn't change throughout the whole time because we're there's no acceleration in the x direction. So that's just 5 meters per second. So that's nice because we didn't have to do any work for that. And I'm all about things that are easy. And then the next piece is we need that final y velocity. So let's go back and look at our formulas. Let me see if I can erase all these x's I made so we can look at this fresh. Okay, so now we need something with a final velocity in it. So we can use this formula or we can use this one. And we won't need that one because that only has an initial. So because we're several steps down into this formula, we can actually use either equation. It doesn't really matter. I personally like to use this one because it doesn't have any squareds in it, so I'm not going to have to take a square root anymore. I don't have to mess with square roots. So I like to use that one if I can, but it's not required. You would get the same answer if you used the other formula. Okay, so here's where we're at. And we're looking for that FVF. Our VIY is 0. And then we just do 9.8 times T, which was 4. So then it's going to be 39.2 meters per second. So that one wasn't that bad either, because our initial velocity was y. If we're doing an angled projectile, that one will be a little different because you would have, you'd have an initial y velocity. But because this one was launched horizontally, you don't have that initial y velocity, so that's a little easier. And then we want the impact velocity. And if you remember, I like to call this the vector velocity because you're going to need the magnitude. So you'll use that a squared plus b squared equals c squared to get the magnitude, and you'll need the angle. And to get the angle, we do the tan -1 y over x. Okay. So again, let's write all the things we know. Again, each time we do this, we know more and more things. And that's why one of the reasons too, they ask for the impact velocity last, because that's usually going to need the most things. I mean, they could ask for it first, but then you'd still have to solve for many of these things anyway. See, look at all those things we know now. I feel so accomplished. So now let's talk about that impact velocity. If you remember this triangle we drew at the beginning, this is going to be 5 meters per second, and then we now have this number, right? 39.2 meters per second. So obviously I didn't draw this triangle to scale. If I'd drawn it to scale, it probably would have looked something like that. But anyway, you don't have to draw it to scale. And so we're basically trying to find this part or the hypotenuse of the triangle. So the first thing we're going to do is do this a squared plus b squared equals c squared. So we're going to do 5 squared plus 30. Let me erase this because I made a dot there. Okay, so the first thing we're going to do is that. And when I put it in my calculator, I got 1561.64 equals c squared. And I'm just going to take the square root of that. And I got 39.5 meters per second is c. So let me think about that and make sure this number makes sense. So it's going to be a number that is, bigger than either of these two, and it's probably going to be closer to this y velocity because that one's larger. Okay, so this number kind of makes sense to me. It makes me think, okay, I didn't do something crazy wrong here. So now let's work on this angle. And a lot of times what I'll see on a test is students will stop here. They'll get 39.5 meters per second for their impact velocity and they'll be done and they'll lose the point for doing the angle because they'll just forget that part. And so what do we have here? We have tangent -1. Our y is 39.2. Our x is 5. And so we get 82.7 degrees. Okay. And this should actually be, if we want to do it right, that would be a -39.2 and a -82 because, we're heading down. We're not going up, if that makes sense. So anyway, that's how you solve that like impact velocity part of a horizontal projectile problem. So as you could see, like I said, there's lots of steps. If we were to do all of these steps on one piece of paper, if you guys are taking notes, you might see that you've maybe filled a whole sheet of paper by now because, there's so much to write. And that's okay. I just kind of assume when I'm doing these that it's going to take a lot of paper and I'm just going to kind of deal with that. So angle projectiles are a little different. And let me tell you how. And we're not going to solve an entire angled projectile problem, but we are going to work on like the very beginning part, the part that's a little different from a horizontal projectile. And the reason we're not going to do the whole thing is just because, these problems are kind of long. And I just kind of plan for that, that they're not quick. So the only difference is for an angle projectile, because you're launched at an angle, you're not going to have, if we think about our triangle, you're not going to have that Vx and you won't get that Viy right away because you're going to get that angled. And so actually it's not even going to look like this. Let me draw you a better picture. Okay. If we have an angled projectile, we're going to have this triangle. It's going to kind of look like this, right? Where it goes up and then it goes down. So we need that that Viy and the Vx, and they're actually going to give you this number. So they'll give you this number, okay? And then right here, our Vfy up here will be 0 because if you think about like a projectile or anything up high, as you're throwing something up, when it gets to the very, 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 very top of its path, it's going to stop for like a split second and then fall back down. And so that very tip top of that projectile's path, the y velocity is actually 0. And so you'll need to solve for the horizontal in vertical components. And you can see that I have done these. Okay. I just have these wrong. Okay. And then the rest of it is the same. So instead of solving for time first, you're going to solve for these x and y components and then time. Okay, you'll want to do those first. Okay, so let's go ahead. Okay, so in this one we have a ball launched at 4.5 meters per second at 66 degrees above the horizontal. So when you have an angled projectile, you're basically given a vector velocity at the beginning. Where in a horizontal projectile, probably remember that was like the last thing you were given. And so this one is wanting the x and y components of the initial velocity. So it's looking for the vx and the viy. Okay, so if we draw our picture, we've got 66 degrees here and 4.5 meters per second here. Okay. Um, and so in order to get our x and y velocities, we're going to do ax equals a cosine theta. And usually when I'm doing these, I'll just go ahead and write them both together. Okay, like this. And in this case, our a is that velocity. Okay, this is basically our a. Okay, so we're going to do 4.5 cosine of 66. And then we're going to do 4.5 sine of 66. Now, there's a really important thing you need to keep in mind. In your calculator, it can switch between radians and degrees. If you are doing these problems with radians, actually any of these vector problems, so if you're doing like the vector resolution, any of that stuff where you're using degrees and your calculator is in radians, you're going to get weird numbers. So when you solve for degrees, you might get something like 0.79 or something like that, instead of like, 75 degrees. I don't know if these are actually equivalent. I just made these numbers up. But if your calculator is in radians, you'll get something like this. And that's how you know that your calculator is in the wrong. It doesn't need to be in radians, it needs to be in degrees. And you need to switch it to degrees so you get, a more normal looking answer for your degrees. Okay. Same thing for these. Since we're dealing with degrees, if you have your calculator in radians, you're going to get a weird answer. Okay. So for this one, this is going to be our VIX, and it's just going to be 1.83 meters per second. And that's going to be our VX, the whole way across. Okay. And then our VIY is going to be 4.11 meters per second. And so remember, that's going to be like our VIY. And then our VFY is going to be 0 meters per second. And that's basically for that half of the triangle. And then if you were to go, if you were to do something for the second half of the triangle, or you needed math for the second half of the triangle, they want you to solve something, you would just make that, that VFY, that would then become your initial. But usually you can figure everything out from the first half, even your time, you can figure out the time it takes for the first half and then, multiply that by 2, or your horizontal distance, same thing. You can find the distance it takes to go this half and then just double that, and that would be your total distance. So there's not a lot of times where you need the full triangle, but just so you guys get an idea of what an angled projectile, it's going to look more like that than something that's launched horizontally. And so that's kind of how we do that very first part of the angled projectile problem. And then you can go, now that you have that problem, those two velocities, then you can go ahead and find the time, find the distance, find the horizontal and vertical components of the as it just hit the ground, and you could even find the final impact velocity if you needed it. So, we just have to do like a pre-step, which is finding these two components, and then we can kind of do the rest of the parts of the angle projectile problem. So, I just kind of wanted to show you guys those today because I think personally, I think projectiles are kind of difficult. And so I wanted to kind of have a lesson on those. And then we'll talk a little bit more about, the 2D motion um, module next week, but I just kind of wanted to focus on projectiles today because they are kind of confusing, and I wanted to make sure you guys had a solid handle on those um, for when you get to your lab and your quiz, and then of course your test.